Okay, so in the last video we talked about what happens when you react a carbonyl with an acid, right? And that's pretty straightforward. Carbonyl plus acid gives us a carbocation or an oxocarbenium ion. In this video we're going to talk about what happens when we react a carbonyl with a base. And it turns out that that is also relatively straightforward and pretty predictable, which is a good thing for us. Okay, so carbonyl plus base. Or nucleophile. And we're going to talk about a couple different types of bases here, or a couple different kinds of nucleophiles. So we're going to talk about hydrogen nucleophiles, H minus. We're going to talk about oxygen nucleophiles, like alcohols. And we're going to talk about nitrogen nucleophiles, which are things like amines. Okay, so first up is hydrogen nucleophiles. So how do we generate H minus? Let's take our we'll use acetophenone this time. Slightly different ketone. And I'm going to react this with lithium aluminum hydride. So lithium aluminum hydride is an ionic compound. So you have a positively charged lithium, a negatively charged aluminum, right? We know that in general, we just ignore the lithium when we do these things. And so really what we have is we have aluminum with 4 hydrogens attached to it. And it's negatively charged. So aluminum is a group 13 element. Group 13 elements are weird because when they have a full octet, as this aluminum does, it has a negative formal charge. And so it wants to get back to neutral. And so in order to do that, it needs to give up a pair of electrons. And so what aluminum hydride is good at, AlH4 minus is good at, is giving away electrons with a hydrogen atom. And so what this becomes is aluminum H3, which is neutral, plus H minus. Right? So whenever you see lithium aluminum hydride, you should just assume, right, this is giving us H minus. So now how is H minus going to react with the carbonyl? Now in the last video we talked about H plus, and we said that the oxygen is the nucleophilic position, whereas the carbon is the electrophilic position. So remember that this oxygen is delta minus, and this carbon is a delta plus. And so the H minus here is going to be attracted to the positive side of things. So the H minus is going to come in and add to that carbon. But of course, that carbon already has a full octet. That carbon has 4 bonds to it. So if we're going to make a new bond to that carbon, that means that something has to break. Right? So think about this like SN2 reaction. Right? In an SN2 reaction, you have your carbon, you have your leaving group, and as the nucleophile comes in and attacks that carbon, the leaving group is kicked out. We get rid of that other bond so that the carbon doesn't have 5 bonds to it. We're going to do the same thing here, only instead of breaking off a leaving group, we're going to break this carbon-oxygen pi bond. Right? So this carbon-oxygen pi bond, we're going to break it, and we're going to push those electrons up onto the oxygen. Right? So this is all one step. The nucleophile adds to carbon. Carbon-oxygen pi bond breaks, and electrons go to oxygen. All right. So what that looks like in the product then is going to be, our benzene ring is untouched, of course. Right. We've made a new sigma bond between the carbon and the hydrogen, so our incoming nucleophile, our hydride, comes in and makes a new bond there, and we've broken a carbon-oxygen pi bond. So what we end up with is the carbonyl is gone, the carbon-oxygen pi bond is gone, and we just have a carbon-oxygen single bond. This step, right, this is called carbonyl addition. We are going to do this step over and over again, like no joke. Between now and the end of this unit, we're going to do a carbonyl addition probably over 1,000 times. So you're going to get tired of me seeing it. I'm going to get tired of saying it. But in the end, this is the thing that you're going to remember from this unit, is how to do carbonyl addition. The nucleophile adds to the the carbon-oxygen pi bond breaks and the electrons go up onto the oxygen, right? So over and over again, we're going to do that. So this is only the first time. All right, so then what would happen is you would quench this with water, or you would add in some weak acid. Usually we just use water. Add in H2O, that's going to add H plus to your negatively charged oxygen, and you're going to get an alcohol out. Okay. So lithium aluminum hydride is a source of H minus, and what it does is it converts ketones to secondary alcohols. Ketones to secondary alcohols. Right, so let's do another quick example of this. Let's say that we'll just do, I don't know, we'll do 3-pentanone. Treat it with lithium aluminum hydride. The H minus is going to come in and attack this carbon. We're going to break the carbon-oxygen pi bond and push those electrons onto the oxygen. Okay. And that's going to create a negative charge in that oxygen, which then we can just quench this with water or whatever, or H plus. Right? And we get a secondary alcohol out on the other side. What happens if we do an aldehyde? So let's use, what aldehyde should we use? We'll use kind of a weird aldehyde here. We'll put a 4-membered ring over there. All right, so lithium aluminum hydride, H minus. Pause the video, pause the video, predict what you think the product will be. I will wait here, I'll still be here when you get back. All right, you're back. Welcome. I hope you got it. So this is not going to be a surprise. The H minus attacks the carbon. We break the carbon-oxygen pi bond. We push those electrons up onto the oxygen. Right, our standard carbonyl addition thing. Oops, I got ahead of myself. It's not OH yet. And we get O minus. Now we got 2 hydrogens there, and so when we quench this and add the H plus to get to a neutral compound, we end up with a primary alcohol. So aldehydes become primary alcohols when treated with lithium aluminum hydride. Okay. You can also use sodium borohydride. Sodium borohydride is much the same thing, right? The sodium is not something that reacts, so it's just the BH4. Boron is another group 13 element, and again, you have the same kind of setup. So BH4 is just another source of H minus, right? So sodium borohydride will also take ketones and produce secondary alcohols. It will also take aldehydes and produce primary alcohols. So you may be wondering, why do we have 2 reagents that do the same thing? The reason is that sodium borohydride works really well. It is very easy to handle in the lab. As long as you don't get it too wet, it'll work great every time. Lithium aluminum hydride is a little less easy to handle. It can, if it gets too dry, it can start fires. And so it's a little bit, it's very, very reactive, of course, but which is a good thing. It can do things that sodium borohydride can't do. And we're going to talk about that when we get to substitution reactions in a little bit. But for now, for ketones and aldehydes, lithium aluminum hydride and sodium borohydride do exactly the same thing. So we'll talk about the difference between them in a future video. But for now, this is hydride nucleophiles, H minus nucleophiles, adding to ketones and aldehydes. We get the carbonyl addition reaction, which is one that you're going to definitely see a whole bunch of times. In the next video, I'm going to get into oxygen and nitrogen nucleophiles. There's not a whole lot that's going to be new there. We're just going to change what our nucleophile is and talk about what that means for us. So tune in for that one. It's coming up next.